In this section, we'll start talking about Rovibrational spectroscopy, which is a special name we give for rotational transitions accompanying vibrational transitions that you see in gas phase spectra. So as always, what we need to be able to talk about spectra is first we need a Hamiltonian. The model that we're going to use to describe rho vibrations, at least in the start, is known as the rigid-rotator-harmonic-oscillator model. And it is quite simply just the sum of these two models added together. Right, so the rigid rotator harmonic oscillator Hamiltonian is a sum of first the rigid rotator Hamiltonian plus the vibrational Hamiltonian, or the harmonic oscillator Hamiltonian. Okay, and because we already know both of these two models very well, it means that we can immediately write down what the energies will be. And in particular, we know immediately that the energies will have two different quantum numbers associated with them. So energy will have a quantum number of n and j, and these energies will be h bar omega n plus a half. Right, these are the eigenvalues or the eigenenergies of the harmonic oscillator, and it'll be plus b times j plus 1, where these are the eigenenergies of the rotational Hamiltonian. Okay, and in this equation we have n can be 0, 1, 2, and so on, and j can be 0, 1, 2, up to infinity. And then just as a reminder, the omega in this is the square root of k divided by mu, where this k is the force constant for a harmonic approximation, and mu is the reduced mass, while b is equal to h bar squared over 2 mu L squared, or h bar squared over 2I, where mu is the same reduced mass. This L is the distance between two atoms in a diatomic molecule, and mu L squared together is known as the moment of inertia. So in both of these cases, so here B has units of energy, whereas omega has units of seconds, or 1/seconds rather. So that this h bar omega has units of energy, and again B still has units of energy. Okay, to write these in terms of wave numbers, we take the original energy expression and then we divide the whole thing by hc. So for example, omega tilde, we take the energy expression h bar omega, and then we divide it by hc. And so this is equal to omega over 2 pi c, which itself is equal to 1 over 2 pi times the square root of k over mu. And similarly, b tilde, which is the corresponding value of b but written in terms of wave numbers, so this will be equal to b divided by hc, and this simplifies to h over 8 pi squared I times c. If we remember from what we talked about previously, the order of magnitude for omega tilde tends to be on the order of 10 to the 3 wave numbers, whereas the order of magnitude for b tilde ends up being on the order of 1 to 10 wave numbers. And this will really impact the type of, or the energy range and the fine details that we see when we look at spectra. So let's take a look at what this looks like as an energy diagram. All right, so what we have here on the right is a depiction of the harmonic oscillator potential with the different energy levels inscribed inside, starting with E of 0, E of 1, E of 2, E of 3. Now, because the rotational Hamiltonian has a much tighter spacing, right, so this is around 100 or 1,000 times smaller spacing between energy levels, that means that there's going to be many different little rotational states that are all packed between any two vibrational states. So this is depicted as having quite a few rotational states that are packed in between here. And so what that means is that for each different eigenstate that you have in terms of the vibrational Hamiltonian, there is also a number of rotational states, and all of the allowed energies are all of these combined, right? So it's every possible vibrational energy plus every possible rotational energy. And so what we end up observing is the energy difference between a state here and then one of these states here. Right, so you move from these total nj to n prime j prime states. And here we can really straightforwardly figure out which transitions are allowed, because this model is based on two simpler models that we already know a lot about, and so we can just combine those results. So in particular, we know that vibrational transitions are only allowed when delta n is equal to plus or minus 1. And furthermore, we know that the n equals 0 state dominates the spectrum because at room temperature we primarily see ground vibrational states. Again, then for the rotational side, we remember that delta j can only be equal to plus or minus 1. But in this case, there is no single predictable dominant j value, or at least we see many j, or in other words, we see this delta j plus 1 for many different starting j values, so not just 0, but also 1, 2, 3, and so on, depending on the molecule and its temperature. Now, the actual RRHO vibrational spectra you end up observing look a little bit like this. You notice this almost symmetric envelope of evenly spaced lines, except for a gap in the middle. And these have already been labeled P branch and R branch. So this is a real spectrum, and now let's go through and derive why this looks the way it does, and also give some context for what the P and R branch mean. Okay, so we'll start by writing out the allowed transitions once again. So remember, for vibrational part, we can assume we're only starting from the ground state, which means that for the vibrational part, delta n can only be equal to plus 1, because we're always starting from the ground state, where we can assume safely we're only starting from the ground state, and there is nothing lower than that, so we can't have delta n equals minus 1. And so this means that the only types of transitions that you can see are those that go from 0 to 1 for the vibrational states. Whereas for the rotational states, delta j equal to plus or minus 1 means that we can see two types of transitions. So j going to j plus 1, or j going to j minus 1. And it's these two types of transitions that will give rise to what are known as the P and the R branch. So let's start with the R branch, which is the one on the right. And the R branch comes from transitions with delta n equal to plus 1 and delta j equal to plus 1. And the energy that you observe from these transitions, so in wave numbers, is equal to the energy of your final position, which would be energy you get from n equals 1 and j is equal to j plus 1, minus the energy of the ground's vibrational state and the jth rotational state. And now if we plug in our values for E tilde, using the fact that E tilde here will be omega tilde n plus 1/2 plus B tilde j plus 1 times j. Okay, so we plug this in, what we get is we have 3 over 2 omega tilde plus B tilde j plus 1 j plus 2, and then this whole thing minus 1/2 omega tilde, still minus B tilde j plus 1. Okay, so if we simplify this together, what we get is omega tilde plus B tilde, and now we look at these two equations, so they both have a j plus 1, so we can factor this part out. And then what you have left is j plus 2 minus j. Okay, so this whole thing just turns into plus 2b tilde times j plus 1. And this will be for j equals 0, 1, 2, and so on. Okay, so now let's look at the p branch, which is going the other way. And so in the p branch, what we have is delta n is equal to plus 1 still, but delta j is equal to minus 1. And so in this case, the observed transition will happen at an energy that corresponds to E of 1, J minus 1, minus E of 0, J, right? Because this is a transition now where N is increasing by 1, going from 0 to 1, and J is decreasing by 1, going from J to J minus 1. And if we plug in our values that we have for the observed energy, this is 3 over 2 omega tilde plus b tilde j minus 1 times j. This is what happens when you plug in j minus 1 to the expression j plus 1 times j. Again, then you subtract from this 1/2 omega tilde, which is the ground state vibrational energy, and then also b tilde times j plus 1. So now when we go to simplify this, we again get omega tilde plus b tilde. And so now what we're going to group on in this next case, notice both terms have a j involved. So there's a j here and a j here, and so now we can write b tilde times j, and then we take the rest out. So this is j minus 1, and then minus j plus 1. Okay, so when we simplify this, what we get is omega tilde minus 2b tilde j. And now this can be seen for j equal to 1, 2, 3, and so on. And the reason that you can't see it for j equals 0 is that this requires you going down a level on j. And if you're starting at j equals 0, there is no lower j value. And so this can only be seen starting at j equals 1. Okay, so if we put these two together, when we look at the R branch first, which I know it's confusing because I wrote the equations for the R branch on the left, but the R branch shows up in the spectrum on the right, but bear with me. So the R branch represents a series of lines with energy greater than omega, greater than the vibrational transition, separated by 2b, or 2b tilde, okay? So that means that the vibrational transition is maybe starting around here. If you plug in j equals 0 to this expression, then this is omega tilde plus 2b. And so the first line in the R branch is at omega tilde plus 2b tilde sitting here. And then there will be another transition for each higher value in j going on. And so there's a series of transitions separated by approximately 2b tilde. Okay, so now if we look at the P branch, which again confusingly I wrote on the right side, so the P branch has energies of omega tilde minus 2b times j, and j here starts at 1. And so that means that the very first transition in the P branch corresponds to j equals 1, and the energy of this is omega minus 2b. So this is a little bit lower in energy than the fundamental vibrational transition. And so that means that this line here is the first transition in the P branch. And then if you go further down the P branch, then these are transitions separated roughly by 2b tilde. A really important point of this is in neither of these do you get a transition with exactly omega tilde, right? You only see omega plus or minus 2b, and you see this here in terms of this kind of missing peak. And that's just because this delta j value must change, right? So you you would only see the omega, you'd only see an omega transition if delta J was 0, meaning that you would have no accompanying other transition. But because we know that delta J must always be non-zero, or must always be 1 or -1, then it means that there will be actually no transition found exactly at omega. Okay, so that's it for this section. Stay tuned for future lessons where we will start to learn why it looks like at the very edges here, the distance between these two peaks is quite a bit smaller than the distance between these two peaks. And this is related to coupling between the rotational and vibrational states. But more on that soon.